We're going to start a new chapter now on random walks. There are a lot of different types of random walk problems that go under various different names. We've seen two. One was the drunken walk, the person trying to get from the pub to home without falling into the river. And the other was the gambler's ruin problem. And we're going to focus the whole chapter here on the gambler's ruin problem and different variations of it. We're starting a new chapter, which is random walks. And we're going to focus all on the gambler's ruin type problems. And so it'll be useful to just introduce all the terminology that we've already seen before. So this is gambler's ruin. And I'm just going to reintroduce the variables and the conventions that we introduced in the previous lectures. So this is a game where there's two players, player A and player B, and we're going to let lowercase a be the number of tokens that player A has at the start. So this is A's initial tokens. So at the very beginning of the game, player capital A has lowercase a tokens. And similarly, lowercase b is going to be the initial tokens of player B. And so we're going to introduce that symbol capital N for just A plus B. It's going to be sort of a boundary condition for us. And we'll say that little p is the probability of player A winning a game, a single game. If you remember, right, the way this gambler's ruin works, player A and player B play a sequence of games, and each game consists of something like a coin toss, something like that. And there's a probability of lowercase p that player A wins that individual game. And if player A wins that game, player B gives player A 1 token. And if player A loses that game, player A gives player B 1 token. So that's the setup here. We'll often refer to Q as just 1 minus p, so the complement of that probability. So this is the probability that player A loses a game. We're going to use the following convention that we've been using for the sample space. So S is going to only start at 1, right? And so it goes 2, 3, and so on. And so this means that the states are labeled by player A's capital after plus 1, right? So this is A's capital plus 1. And the reason for the plus 1, again, is so that when we talk about one-step transition probability matrices, the element in the top left corner of the matrix will have index 1, 1, because we're going to use these states as the actual indices for the matrix. All right, and so the initial state, so x0, that's going to be lowercase a plus 1, right? So x, which is our chain, that's the number of, well, let's just write this out. So in general, x sub t, this is equal to A's capital after game t, or sorry, after, well, you could call it game or time. And so, of course, then t has to be greater than 0. We've already defined x sub 0, but so it's this plus 1. Okay? And so another way to write this is in terms of the random variable that represents the winning or losing of the game by player A, we say x sub t is equal to, let me rewrite this. We say x sub t is equal to the previous one, so x at t minus 1 plus z sub t, capital Z. And so in this way of doing things, we're requiring t be greater than 0. The condition at time 0 is just that x is a plus 1. And so as you increment forward, you have to look at this random variable z, which tells you whether or not a wins the game. So in other words, z is a random variable, and it's plus 1 with probability p. And it's minus 1 with probability q. Okay? And the way the game works is you keep playing until somebody's ruined, right? So play, keep playing more and more games. So play until some particular time at which everybody's ruined. So either xt is equal to 1, which would mean player A is ruined, right? If its total number of tokens, player A's total number of tokens plus 1 is 0, or is 1, then that means player A's tokens is 0. Or xt is equal to n plus 1, which means player A's number of tokens is n, which is a plus little b. Okay, so now we can just remember, recall what the directed graph looks like for this problem. Off to the left, there's state 1. That's a state where player A has lost everything. And then 2, 3, and so on. And it goes all the way up to, we'll say, n, and then n plus 1. And this state over here is the place where player A has won everything. And these two ending states are sort of special. So over here on the left, if you get into state 1 and tried to play again, you just return to state 1. Player A has no more tokens to give over there. And so the game is over. There's a probability of Q for going from state 2 to state 1. So state 2 is where A has just got 1 token left. And should they lose, then the game is over and you're in state 1. There's a probability of P for going from state 2 up to state 3. So that's where player A goes from a situation of having 1 token up to having 2 tokens. And there's a probability of Q again for going from state 3 to state 2. And this just cycles over and over again. Until you get to the end. So we've drawn this before, but just want to remind you. And at state n plus 1, there's a probability of P at state n for getting up into state n plus 1. And then that's the end of the game. So we put this like this. Right? So this is what the directed graph looks like, and we've seen it before. And the classes for this are, the communicating classes are, there's 3 of them. We've talked about them before, I think. So the first one is just state 1. It communicates with itself. That's it. I don't think we've looked at these actually. So I don't think we've written down the communicating classes for this. So everything forward, 2, 3, and so on, those all communicate with each other. So D2 is equal to 2, 3, and so on, up to n. It's possible to go from any one of those to any of the other ones. And so that's the communicating class number 2. And then the third one, is just n plus 1. It only communicates with itself. So for these guys, D2 is the most interesting set of states. D2, we call this the transient class. Right, now transient states are states that you might not return to, right? So if you're in a place where A has 5 tokens, it could be that you get more tokens, or player A gets more tokens and eventually comes back to having 5 tokens, but doesn't have to. They might, right? And I think we've looked at the probability, one-step probability transition matrix for this. One-step transition probability matrix. But I'm just going to sketch it out. So the probability of going from state 1 to 1 is 1, and then it's all zeros after that. Going from state 2 to 1, that has probability Q. Going from 2 to 2 has probability 0, and 2 to 3 has probability P. And then 3 to 1 can't happen in one step, but 3 to 2 can happen with probability Q. 3 to 3 can't happen in one step, and 3 to 4 can happen with probability P, like this. And so this carries on until you get to the last 2 states, last 2 rows, which look like this. They finish like this: Q, 0, P, and then 0, 0, 1. Right, and so that's what this matrix looks like. I think I made this too short. Too long now. Oh man, can't get a break. So this is what this thing looks like, and it's n plus 1 by n plus 1. Right? Now, you could try to write this in a funny notation. I don't know if people use this, but I find it handy. You could write it like this. It's sort of a diagonal matrix, but not quite. And so you could write it in this very funny notation. You could say the first row is 1 on the diagonal. The second row on the diagonal is 0, but so I'm going to write the things that I know, which are Q, 0, P. And that's centered on the diagonal. And then the third row is also Q0P, centered on the diagonal. And so on, up until you get to the last one, Q0P, and 1. I think that's an unconventional notation. I don't think people use that so heavily, but I think it's kind of handy. You might find it useful. It's a little bit of a simplification sometimes. Rather than trying to write out this whole matrix here, this is sometimes more useful. All right, we're going to introduce 2 more probabilities that we're going to try to calculate. And the first one we'll call capital W. And in principle, it's a function of little a and little b, or you could say little a and n. It's equivalent. And this guy's going to be the probability that A wins the overall tournament or match. I don't know what you want to call that exactly, but the collection of games. In other words, the probability of B being ruined. And given the boundary conditions that player A started with lowercase a, and that the total number of tokens was capital N. Right, so let's write that out in words. So this is the probability that player A wins, I don't know what you want to call this, tournament or match. Right, the overall collection of games, given A starts with lowercase a tokens, and B starts with n minus a. Oops. Which is lowercase b. It doesn't appear in the equation there, but right. So we're going to try to work that out. That's going to be one of our target calculations, and you can write this as a more formal statement. So let's say this is the probability that there is some time t such that x lowercase t is equal to n plus 1 for some t. Maybe you should put there exists some t such that. That's another way to do it. We should say greater than, well, yeah, that's fine. Given that x0 is a plus 1. In other words, given that player A starts with lowercase a tokens. So that's just a more formal, a more explicit way to write it, so there's less confusion. All right, and then the other probability that's kind of interest is just the complement of this, and so we'll call that capital R. Similarly depends on A and N. And this is just so it is defined to be the complement, so it's just the probability that A will lose the match. Or you could say all this same stuff again and just reverse A and B. So this is the probability that A is ruined. Right, and so you can write out a formal statement for it, or you can just define it like 1 minus W. All right, and so these are the two things that we're going to try to calculate for a variety of different conditions. All right, now that we've got the definitions down for the things that we want to calculate, we're going to operate in true mathematician style and just tell you the answer and then prove it. So we're going to tell you the answer in the form of a proposition. And I'll just write it down here. So the probability of A winning looks like this. I'm going to need a little bit more room here. So there's sort of two cases, it turns out. One is the case where P and Q are the same. So the case of a fair game, I guess you would say. If they're the same, they're both a half. That one is relatively easy, so I'll write that down first. So if P and Q are the same, the answer is just little a over n. And you could probably have guessed that. So this is for P equals Q equals 1/2. But if they're not the same, you get a more interesting result. And it looks like this. So it's a ratio. On the top there is 1 minus Q over P to the power A. And then in the denominator, we've got 1 minus Q over P to the power of capital N, or A plus little b, if you wish. Put that again. Okay, and so that's the result if P is not equal to Q. Guess we don't have to write if there. And so this is the claimed result for how this thing goes, and we'll work it out. We'll do a little proof of it, but before we do that, we'll just write down as a corollary what is the probability of B winning, which is just the complement of this. So as a corollary, R as a function of A and N looks like this. And you can just work it out, of course. So if P and Q are the same, it's 1 minus A over N And if they're different, so the only thing that's funny here is I'll just do the algebra for you. So up in the numerator, there's q over p to the power a minus q over p to the power n, all divided by 1 minus q over p to the power n. And this result, you know, it's not that exciting once you've seen the first one. It's just a little bit of algebra. All right. Now let's think about what these are fine. It's useful to kind of look at these though, I think, because it gives you an impression of what you're seeing. What are these equations? What do they actually look like if you were to say plot them? And so I'm going to kind of sketch what the plot ought to look like for w as a function of a and n versus a, like this. And let's say we do a special case, a special case of, well, we have to pick a value, so let's try the n equals 5 case, right? So if n is 5, what's the largest value that we can have for the initial number of tokens for a? That's also 5, right? That means b has no tokens at the start. And it's useful to sort of think about that. So what is the probability of a winning if you start off with b having no tokens and a has all of them? Well, if that's where you start off, a has already won, and so the probability of a winning is 1, and so it should be over here, right? And so what I want to try to imagine is what kind of shapes do you expect, what kind of curves do you expect for w as a function of little a? And you get different results depending on, if you can look at these equations and see, depending on the value of p. But so if p and q are the same though, so if you're in this situation, you don't get any different result. You just get a slope, a straight line with a slope of 1 over n. And so that should look like this. Oh no, I've just erased everything. Work that straight. And so this is the p equals q case. Just a straight line. And then you can ask yourself, like, what happens to this curve as I increase p? You know, it's think to yourself for a second. Just sort of label this. Right. So as you increase p, it should be sort of easier for player A to win. And if you decrease p, it should be more difficult. And so what does it look like for things to be easier? Well, if it's easier to win, then this curve, as you come off of here out of 0, it should sort of rise quickly, right? And it's got an asymptote at 1. So something like that, right? Oh, and I probably should have said, this place over here, this is if player A starts with 0 coins or tokens, then the probability of winning is 0 because player A starts the game having lost. And so you start, so if you increase A when P and Q are the same, it looks like this. You just grow, your chances of winning grow linearly with A, with the number of tokens that you played with. So that's kind of interesting. What do your chances of winning look like if you increase P if you increase A for different values of P? Well, you have to look over here, this thing here. And I find the plot kind of handy because this thing, when I just stare at that equation, I don't see the result immediately. You can certainly see what happens. So if Q over P is less than 1, you can see you can get kind of limiting behavior as A grows. But nevertheless, we sort of expect this thing to kind of have some sort of curves like this. So basically, increasing P should move your curve this way. If you think of it as like a guitar string held between two pegs, then as you increase P, you should sort of pull that string out. So this is sort of something like this. So we'll say larger P. And of course, you should have a limiting behavior. If P is equal to 1, then what's the probability of A winning? Well, there's sort of only 3 numbers that are of interest. If you start with A, you still have to have this point over here, because if you start having lost, you've lost. But for any other starting value, the probability of winning should be 1, and so there should be some kind of limiting curve that's way up, just like this. Almost a perfectly straight line, and then another perfectly straight line that looks like this. And so this should be for P equaling 1, or the limit. Like, it should do something like that. And similarly, if you had P close to 0, you should have something that looks like this. And so adjusting P is like pulling this string, if you think of the curve as the string. And so I plotted these on a computer, just so you can get an accurate picture rather than seeing my hand-done drawings, and you'll see the results. Where are they? Here, I think. Yeah, so it looks like this. So I'm going to just take these and bring them over to the lecture where we can discuss them. Thing got a little bit clipped. I'm not sure why. So we'll paste that into here. Doesn't have to be as big as it was. All right, so this is done on a computer. So if you just plot them on a computer, you should be able to do that. I think everybody here should be able to do that. Just pick a range of A values. And can you tell what I use for N here? Well, you should be able to. It's also kind of, I gave it away because it's the same as up there. It's N is equal to 5. And you can see that it is the case that as you increase P, you kind of pull this string up like this. So that's what it looks like with P equals 0.9. And you should, as a test for yourself, try to reproduce the curves for P smaller than a half. And I think you can kind of imagine what they look like. It should look similar where you kind of pull this string down towards this way, right? And so you should get sort of the reflected. There should be a curve like this, somewhere over here, another one, and so on for different values of P. And so you should probably do that as just an experiment for yourself to see if you understand what these curves actually look like. It's also worth pointing out that, like, this is the probability of A winning. But so if you picked one particular value, so I don't know, let's say we had this particular. Let me plot in a different color. Let's say you had this value of A here, which looks like it's about, I don't know, 0.6 or so. Then the probability of winning for A would be around, I don't know, 0.38 or so, or 0.37, I don't know, something like that. And so if this is the probability of A winning, then this is the probability of B winning, just this excess up here. And so you should be able to work through that. And I really should add that these curves, they're not really curves. They should actually just be a finite collection of points. So what I mean by that is the probability of A winning could in principle be anything, but it has fixed values that are kind of possible limited by A. A can only be discrete numbers of coins, right? So player A cannot start with a half of a token, or sorry, I keep saying coins. Player A cannot start with a half of a token. They can only start with 0, 1, 2, 3, 4, or 5. And so that's why I put these little dots on this curve. These are the only sort of meaningful values for us for this particular version of Gambler's Ruin. These discrete valued things. But you could certainly imagine some non-discrete version of this. And how does this work? It's more, though, than just allowing different values of initial tokens, because it's still the case that winning or losing results in changing your number of tokens by one discrete value. So it's a little bit non-obvious, like what is the meaning of these kind of like areas in here. You really should just be looking at individual points here. But I somehow find the curves illustrative, like this imagining pulling of a guitar string. I find that kind of useful. So that's what those little dots mean. All right, so that was just going over what is the answer, right? Let's go through the proof, or if you wanted to, you could just start with this to see how would I ever figure this out. But so we're going to go through with a proof here. Right, I'm going to move it down. There's like a page barrier there for me. Right, so how can we show that this is true? And the rest of this lecture is just to show why this works out, this proof. So to simplify the proof, I'm going to create an event. I'm going to name the event V, like for for sort of victory. So let's say let V be the following event. So V is equal to this sort of statement. Xt is equal to n+1 for some t greater than or equal to 0. Right? So that's what the event V stands for. That's going to save us a lot of space when we write things out. Right? So let's just write out the left-hand side that we're trying to prove the probability of A winning. Right? And so we can write that in the following way. We can say, well, that's the probability of the event V given that x0 is equal to A+1. Okay, so now what I want to do is sort of expand this right-hand side using the total probability theorem, just this, where the event that I'm going to kind of condition on is just what happens at game 1 as a result of game 1. And so we'll just write this out and kind of discuss what it means or why it's useful as we go. So this is the probability, the same thing. This is going to be a sum. So it's a sum. I'm using the total probability theorem. And I'm going to say K, which represents what happens after game 1 or during game 1. It's either plus or minus 1, right? And I'm going to say the probability of V, or victory, given, and then these are the two kind of, what's here is Z, so the outcome of game, or whether or not you go up or down a token on the first game, that's equal to K, so it's plus or minus 1, given that you and that x0 was equal to A+1. Right, so that's using the total probability theorem. Then I got to put over here the other probability that Z1 is equal to K, given that x0 is equal to A+1. Right, now Z1 doesn't depend on what x0 is, so writing that given part, the conditional part for the second term there is kind of irrelevant. And so let's sort of clean this up a bit. And we can also kind of clean up the first term. So we'll say this is a sum over K. Then we have the probability of V given. And so I'm going to rephrase things not in terms of Z, but in terms of X. Right? So I'm going to say given that X1 is equal to what? So if Z1 is equal to K, X1 is equal to A+1 plus K, right? If it's also true that x0 is equal to A+1. And then this second probability, I just write this as, just drop the conditional part. Right? And the probability that x0 is equal to A+1 is 1, because it's just the starting condition of the game. Okay, and now we'll use the Markov property or the memory list property to try to shrink this a bit. So we're gonna strike this off of here, right? So I'll just do that with my handy eraser. So because of the memoryless property, so I'll just write this over here. The probability that x1 is equal to a plus 1 plus k, and that x0 is a plus 1, or sorry, let me restate that. The probability of victory given that x1 is a plus 1 plus k, and that x0 is a plus 1, is the same as just the probability of victory given that x1 is equal to a plus 1 plus k. The information about what was going on at step 0 doesn't influence that probability. If we know that after game 1, you've got x1 is equal to a plus 1 plus k. So we shrink that down like that by the memoryless property. All right, now we can rewrite this. K is only has 2 different values, right? So fine, so we don't really need a sum. That's a little excessive. We can just write out the 2 different terms. And I want to do that and then sort of analyze what these different things look like, right? So here we've got, so when k is equal to minus 1, right? So this is k is plus or minus 1. The first term then, if k is minus 1 for that one, is probability of v given that x1 is equal to a, right? And then times the probability that z1 is equal to k. Z1 is equal to, let's think about this for a second. I was going to write in there the probability that z1 is equal to minus 1, but we have a name for that, right? That's the probability of losing a game. So that's q. And then we've got the probability of v given that x1 is equal to, and now I'll put k equals 1, so I get a plus 2 times p, right? So if you think about, you can put this is an instance where you maybe get a little bit of a help by kind of putting this into words and seeing what this says. So this is saying that first term there, right? The q is the probability of losing a game, right? So let's write that out. Probability of losing a game times this other thing, which is the probability of victory or winning the match when you started with an initial value of capital of not a, but a minus 1. If by initial here we mean at time 1. So this is probability of win match. It doesn't really matter that you're at step 1 here, really. But so you say probability of winning the match with initial capital of a minus 1, which is the way I'm kind of reading this, right? Initially, from this thing's perspective, is that you've started. It doesn't matter what was happening earlier, but if you're at time step 1, you can kind of call that initially. So you're starting the game, and if x1 is equal to a, that means player A has capital A minus 1 at that point. All right, and then so that's just reading this term here, right? So the q is here, and then this guy is here, right? And then the second term looks similar. So we have the probability of winning a game, a single game, that's the p, times the probability of winning the match with initial capital of not a plus 2, right? We got to shift things, so this is a plus 1. Right? Now, these things here, we have names for these. or we have a formula for this, right? Winning a match given some initial capital. That's W, right? So we've got W's on the right-hand side, which is going to help us out, except that things are shifted somehow, right? So we're talking about on the left-hand side, what we're working toward is the probability of victory given your initial capital was little a. And on the right-hand side, what we have is the probability of victory given two different values of initial capital, a minus 1 and a plus 1. And so that's how this looks. And then over here, this is, oops, that's Q, and this guy's P. Okay, so if you think this through, this should if you might have to look at that line several times and kind of read it to yourself, make sure this makes sense to you. But so what we've got is Q times W winning match with initial capital of a minus 1, right? So that's a minus 1 n, right? And then plus probability of winning a game, so that's P, and then times probability of winning the match given that you started with capital A plus 1. Right? Now, this is sort of, not sure how much experience you guys might have with these, but these are a discrete version of differential equations that go by the name of difference equations. And you may have had experience solving these before or not, and that's okay. We'll work through how to solve this. But if you have had experience with this, you might know how to you might have a lot of, just like if you've never seen a differential equation before, it's a bit of a mystery how you go ahead and solve it. But if you've had a couple of classes on how to solve them, you already have a bunch of tools in your toolkit. The first of which, of course, is the best one, guess the solution. But then you might have a bunch of other tools, like try some different representations of things, to maybe do some transforms, or I don't know, a bunch of different things for how to solve them. And similarly, there's a set of tools for solving difference equations. So you could solve this formally as a difference equation and get W as a function of A and N. That's fine. You could also instead, so this is a difference equation. You could solve it formally. And by that I mean like with a bunch of tools that you've built up over the years, say. Or you could just work it through like what we're about to do here. Right, which is also a solution, but it's sort of like, if you don't have a lot of experience with these, this might make more sense. All right, so the first thing I'm going to do is I'm going to redefine, there's a lot of W, A minus 1, and comma n and stuff like that. So we're going to kind of simplify the notation. So we're going to define a W with a subscript of A. So this is that's my symbol for define to be 3 lines there. This is going to be W A comma n. And this is going to sort of simplify how our equations look a little bit. All right, and so we can rewrite, so we can write the above difference equation as follows, right? We'll say the left-hand side is W sub A, and we're going to sort of cleverly multiply that by 1, ingeniously, P plus Q times WA. So that the P plus Q is just 1 there. And then if you look at these, so we've got Q times WA minus 1 plus P times WA plus 1. All right, now we'll just move things around a little bit, put things multiplying P on the left-hand side and things multiplying Q on the right-hand side. So we've got P times WA plus 1 minus WA is equal to Q. So I'm moving things, maybe you should be able to see what I've done there, I think. times Q times W sub A. I've sort of swapped what I mean by left and right there. Minus W sub A minus 1. Right? Okay, and we keep messing around with this and write this as, so we bring the P over to the other side, and I've got WA plus 1 minus W sub A is equal to Q over P. Now you see why this ratio is going to show up a bunch, times what was already there, WA minus WA minus 1, right? Now we're going to notice our boundary conditions, right? Which we mentioned when we were looking at the plot. Right, so what are our boundary conditions? If only I could spell, huh? So what are the boundary conditions for W? What could W be if you started off with no capital? So A was equal to 0. And what would W be if you started out with capital N? If A's capital was capital N at the start of the game. Right, so these are the boundary conditions. Right, so if you started out with nothing, your chances of victory are 0. And if you start out with everything, you've already won, and your chances of victory are 1. Right, so these are our boundary conditions. Right. I also want to just start stacking these up. So now I'm going to do this kind of clever, I don't know if it's clever or not. But let's start just writing these things out. All right, so we'll start from A equals 1. All right, and just start writing this out, and then we'll increment up. All right, so on the left hand, let's put A equals 1 case over here. And what I get, I don't know, maybe I want to write this. So make a stack. Stack some equations. Stack things. Stack things up. All right, so the A equals 1 case. Right, so if you started out with 1. Then what this says is, this meaning this line up here that we were just at. So you get W sub 2 minus W sub 1 is equal to Q over P times W sub 1 minus W sub 0, right? But our boundary conditions show up here in one place. W sub 0 is equal to 0. So I'm just going to erase this, right? And so this is what we get, right? Now let's look at the A equals 2 case. Right, and I get W sub 3 minus W sub 2 Q over P and W sub 2 minus W sub 1, right? Now, if you stare at this for a while, the left-hand side, W sub 2 minus W sub 1, right? It shows up right over here, right? So I could take this thing and substitute it in there, right? And so let's just do that. Oops. W sub 2 minus W sub 1 is a known quantity. It's Q over P times W1. So if I substitute that in, what I get is Q over P squared times W1, right? Now, if you keep repeating this over and over again, make this stack go on and on and on, what you wind up with, and you might need to do a couple more, I don't know, you might need to see, but you can just build this up over and over and over again until you finally get to W A plus 1. And so what is this case here? So this is the last one, right? Minus WA. And this is equal to Q over P to the A times W1, right? So in other words, if you look at this thing here, right, you've got, how do I do this? 3, 2, 1, and then here's the power is the 2. And so that's like the 3, that's like the 2, shows up as the power, and that's like the 1. Hope that's clear. It's the same as the 1. That one is the 1. Okay, so we make that stack, right? Now, look at this as just like this giant addition of equations. Right, so add things up. Add equations. Right, so working down from the top, right? When you add these equations up, on the left-hand side, almost everything disappears, right? So this guy is going to balance with that. And similarly, W3 is going to balance with a term minus W3 over here like this. So all this balancing is going to occur. This guy is going to be balanced by something up here like this. And so the left-hand side is going to look like this. WA plus 1, that one's going to survive, right? And then minus W1. And the right-hand side, when you add all these things up, so all the terms look like this, right? And when you add all those guys up, what that looks like, so that's a sum. So the W1 is common to all of them. A sum from k equals 1, oops, sorry. Why won't you erase? K equals 1 up to little a of q over p to the k. Right? I think that should be okay. And now we just move things around. Right? So WA plus 1 on the left. And I move W1 onto the right-hand side. And so I've got W1 times this sum, 1 plus the sum I had before. And if you look at that, that's clearly, I can rewrite that sum as starting from 0, right? Because q over p to the 0 is 1, right? And so I've got this guy is equal to W1 times the sum over k equaling 0 to a of q over p to the k. All right? Okay, now, we've got sort of two different cases here, all right? And so this is a geometric series, of course. So I guess I'll fill in the left-hand side, WA plus 1, right? There's two different cases here. This is a geometric series where the ratio is either 1, which is a sort of a peculiar case, right? Well, it's not a problem. It would be in principle a problem if A were infinite, then the thing would diverge. But if A is equal to 1, you get a different result than if A is not equal to 1. And so if A is equal to 1, so let's look at these things. So two cases. This is a geometric series. Right, so this sum oops, just steal it. Should have done that before. Right, so this is equal to a bunch of two different cases. So A plus 1 if q over p is 1. Right? And if q over p is not 1, you get 1 minus q over p a plus 1 over 1 minus q over p. Right, so these are the two cases for the geometric series. You get kind of a special result for the geometric series. I mean, this equation you should sort of recognize, but the geometric series equation is sort of funky when the thing that you're making powers of is actually 1. You can see it makes trouble for that thing down there. Okay, now we're going to evaluate the two different cases here and finish each one separately. So first we'll do the special case, so the P equals Q equals 1/2 case. And then we'll finish solving the equation. So when that's true, what you have is, so I'm looking at this equation here, WA plus 1 is equal to W1 times A plus 1. Right, now what we want to do is sort of somehow exploit the boundary conditions, right? And so I want to evaluate this at a place where I'll be able to exploit the boundary condition. And the boundary condition I want to use is the one I haven't used yet. I want to use this boundary condition here, W sub n is equal to 1, right? So I want to evaluate this at A plus 1 is equal to n. Right, if I do that, the left-hand side is W sub A plus 1, that's equal to 1. So using W sub n is equal to 1. So I've got 1 is equal to W sub 1, and A plus 1 is equal to capital N. Right, that was the condition that we just enforced. And so this gives us the expected result. W1 is 1 over n. Now, if I put, well, it's not quite the expected result just yet. I put this back in, right? So take this thing here and substitute it back into here. And so substitute back. And I've got WA plus 1 is equal to A plus 1 over n, right? Now, I can just rename the index A plus 1, just rename it A, and what I get is the expected result. W sub A is equal to A over n, right? So that's the promised result for the special case where the probability of A winning is 1/2. So now we can carry on with the general case, the more common case, the one that makes all those more interesting curves, the pulling the guitar string back, or the violin string, or whatever it is. So this is the P not equal to Q case. This is the general case. And we're going to use the same sort of trick, all right? So first of all, I'm going to take the result, right, from up here. So this is the way the equation looks. On the left-hand side is WA plus 1, W1 times this whole mess here, right? So why don't I just copy that? And on the left-hand side, it was WA plus 1 is equal to W1 times all that stuff. Right, so that's what the equation looks like for the general case. That's taking the result, taking the geometric series. All right, and we'll do the same kind of thing, all right? Exactly the same treatment. So how did I even phrase it up here? Evaluate at A plus 1. I can even just steal it, all right? Evaluate at A plus 1 equals n and use this boundary condition. Right? So if A plus 1 is n and Wn is 1, then the left-hand side is once again 1, right? And I've got W1, and then on the right-hand side, what have I got? A plus 1 is n, right? And so I've got 1 minus Q over P to the n over 1 minus Q over P. All right, so if we just solve this for W1, W1 is equal to 1 minus Q over P in the numerator over 1 minus Q over P to the n in the denominator. And then following what we did before, exact same strategy, we're going to take this thing, substitute it back into here, And then we're going to do some reindexing to turn that into A. All right, so we'll substitute that thing back in there, and what we get is WA plus 1 is equal to, I'll just copy it and save us some trouble, this guy, I'll take it from up here, times this guy, right? And you can see that this numerator cancels with this guy, and we've got the result 1 minus Q over P to the A plus 1 over 1 minus Q over P to the N. And now the last thing to do is just to reindex things so that you replace, just make a new name for the index A. And so we get the expected result. W sub A is equal to, and then I'll just copy this guy. Oops. And I don't need the plus 1 anymore. All right, that completes the proof.